Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi and good morning. Today we will continue our discussion in electronic circuits 1. We already discussed about the chapter 5 BJT AC Analysis for part 1 last week, and today we will continue to BJT AC Analysis part 2. Okay, we already discussed about the RE model and hybrid V model in last week. So today we will continue for another configurations called a common emitter voltage divider bias. Last week we already discussed about the common emitter fixed bias. Okay, as you know that common emitter voltage divider and a fixed bias, the differences is in voltage divider we have another resistor. We have two resistors here, R1 and R2, so it will divide the base voltage through the base terminal here. Okay, so if we draw, and then we also introduce the emitter resistor here and connect to the bypass capacitor. We already discussed about the bypass capacitor in last week, and what is the function of the bypass capacitor and what is the value of the bypass capacitor. Okay, so if we want to use the RE model to draw the voltage divider, we can draw like this one. This one is base terminal, this one, and then this is the collector terminal here, and then this is the emitter. This is the emitter. Okay, because of in AC analysis, the bypass capacitor is short. Okay, short. So it's like the emitters connect to ground. Okay, connect to ground like this one. This means that it is short. So we didn't calculate the emitter resistor here. Okay, this is the emitter resistor we remove in AC analysis. Okay, so we connect in AC analysis procedure. We connect the VCC to the ground. So the R1 and R2 here is connected to the ground, become the R accent here. So R accent is the parallel of the R1 and R2. And then for the RE model of BGT, we have the beta RE and then beta IB and then RO for output resistance. And then the output is collector capacitor here. Okay. So the input impedance here ZI and then output impedance here is ZO. For the ZI, we know that ZI is the parallel of the R1 and R2 here. So the R accent, this one, R1 is parallel to R2. So the Z input impedance, this is the parallel. This one is parallel of these three resistor here. So input impedance of ZI is R accent parallel to the beta RE. And then for the output impedance, the ZO here is the parallel of the collector resistor and then the output resistor here. RC parallel to RO. Okay, and then ZO is equal to RC when the output resistance small RO larger than 10 RC. And then for the voltage gain, we have that AV VO per VI is minus RC parallel to RO per RE. And then when the RO is larger than 10 RC, AV become minus RC per RE. So this is a minus, it means that this is the phase shift between the output to the input impedance. And then for the current gain, IO per IE, we can use this one, beta big R accent, RO per RO plus RC multiply by R accent plus beta RA, and then we can do the simplify for this one. When the RO is larger than 10 RC, so we can so this one become the RO, and then we can remove this one, so it's become beta R accent per R accent plus beta RE. So when the RO is larger than 10 RC, and then when the R accent is larger than 10 beta RA, so we got that current gain AI is become to beta. And then if we have the voltage gain and we want to calculate the current gain, we can use this equation. AI is become AV minus AV ZI impedance per RC. Okay, so this is the example. So for this circuit, determine RE, ZI, ZO, and AV. And then the parameter of part B when the RO is 1 per HOE is 5 kilo ohm, and compare the results. So the first one, we have to determine the RE. So how to determine RE? So we have to do the DC analysis because of the RE is 26 millivolt per IE. Okay, so we have to determine the current emitter here. So for the first one, we have to test when the beta RE is larger than 10 R2. So here, okay. So if we can, if this is satisfied, we can use the approximate approach, like I mentioned in this BJT DC analysis. We can using the exact approach and approximate approach. Approximate approach, we can use approximate approach when the beta RE is larger than 10 R2. Okay, so RE is 1.5 kilo ohm and R2 is 8.2 kilo ohm. So if we multiply beta with 1.5 kilo, we got that 135 kilo ohm larger than 82 kilo ohm. So that's why we can using the approximates. So in the approximate, we determine the VB. VB is R2 per R1 per R2 dot VCC. We can got that VB is 2.81 volt. So this one is emitter, this is the base, and this is the collector. So we got that VB is this one. So VB is 2.81. And then how to determine the VE? VE here. So VE is VB minus VBE. Why? Because VBE is VB minus VE. Okay. So VBE is here. This one is VBE. Plus minus. In silicon is 0.7. So we got that VE is 2.81 VB minus 0.7. We got that 2.11 volt. And then IE here is VE. IE is VE here per RE. Okay, so we got that VE is 2.11, RE is 1.5. We got that IE is 1.41 milliampere. So RE is 26 millivolt per IE, got that 18.44 ohm. And then number B is the Z1. Okay, we know that Z1 is the parallel of R1, R2, and beta RE. So the first one, we determine the R accent. We got that R accent is R1 parallel to R2. We got that 7.15 kilo ohm. And then ZI is RI parallel to beta RE. So we got that 1.35 kilo ohm. And then C is ZO when the RO is unlimited. So we got that ZO is become similar to RC is 6.8 kilo ohm. And then the last one, AV, when RO is unlimited. AV is, we got from this one, minus RC per RE. So this minus 6.8 kilo ohm per RE is 18.44 ohms. So we got AV is minus 368.76. Okay, so if we have the RO is 50 kilo ohm, so Z1 become, so we have to, Z1 is similar because in Z1 we didn't calculate the RO, so Z1 is similar 1.35 kilo ohm. And then for ZO, the first, this is the RO is unlimited. If the RO is 50 kilo ohm, so we have to make a parallel, become the RC and RO, because that's 5.98 kilo ohm. And then for AV, minus RC parallel to RO per RE, so we got that minus 324 per 3. So because we follow this one, so we have the RO here, so we follow this equation. Okay, so we notice that if the output resistance is unlimited, so the AV voltage gain become larger, and if the RO is not unlimited, it's like the 50 kilo ohm, so the AV become lower than if the RO is unlimited. So the ideal BJT is the RO is unlimited, so the AV is very large. Okay, and then the next configuration is common emitter bias configuration. In this one, we have the fixed bias, and then we have the emitter resistor here. So we connect just emitter resistor here. Okay. So we call that emitter bias configuration. If we draw in the RA model, become this one. So this is the RB here. This is the RB. And then we have, this is the model of the BJT. And then this is the RE here. This is the RE. Connect to the emitter. This is the emitter. And this is the base. And this is the collector. So this, between the emitter to the ground, we have the RE here. And then we have the RC here. Okay, we have input impedance here, and then output impedance here, and then we have the base impedance here. Okay, and then for the input impedance, the Z1, ZI is the RB here, parallel to ZB, the ZB. Why we have the ZB here? Because of the ZB is content of two resistors. The first one is beta RE, and the second one is this one, the RE. So we have to calculate emitter resistor here. And then ZB is beta RE plus beta plus 1 RE. Okay, so ZB is beta RE plus RE because of the RE is larger than RE. So we can call ZB is beta RE, beta dot emitter resistance. And the output impedance is just RC here. Okay, so the output impedance is ZO is equal to RC. And then the voltage gain, the AV is VO per VI is become minus beta RC per ZB. And then so the AV become RC per the ZB is the beta RE here. Okay, so we can remove the beta here and beta here. So we got that RC per minus RE plus RE. So because of the RE is larger than our small RE, so we could get AV is minus RC per RE. Okay, and then this is the common emitter is phase shift. And then this is the current gain. AI is IO per I1, beta RB per RB plus ZB. Okay, so the current gain for voltage gain is I is minus AV ZI per RC. Okay, so this is the network of the emitter resistor. Okay, for the network without CE unbypassed, determine the RE, ZI, ZO, and AV. So the first one, RE, so we have to use the DC analysis here. Okay, so IB is VCC minus VBE per RB plus beta plus 1 RE. So how to determine this one? So please looking for the DC analysis of the BJT. Okay, so you can get these equations. So we got that IE is become 4 beta, IE is beta plus 1 IB. So we got the IB from this one. So we got that IE is 4.34 milliampere. And then RE is become 26 millivolt per IE is become 5.99 ohm. And then we test for the B is a ZI. So we test the RO is larger than 10 RC plus RE. So we got that RO is larger than this one, 10 RC plus RE. So we can got this one, ZB is equal to beta RE plus big RA. So we got that ZB is 67.92 kilo ohm. So the ZI is using this equation. ZI is RB parallel to ZB. So we implement in this equation. ZI is RB parallel to ZB. So we got that RB is 470 kilo ohm and ZB is 67.92. So we got that ZI is 59.34 kilo ohm. And then ZO here is equal to RC is 20.2 kilo ohm, and then AV is VO per VI minus beta RC per ZB, like this one. Sorry, this one minus RC plus RE. Okay, so we got that minus 3.89. Okay, and then repeat the analysis with the ZE. If we connect CE here for the bypass capacitor, okay, so the DC analysis is similar. So the RE is 5.9 ohm, and then for the ZI, because of the emitter resistor here is short because of the CE, so the ZI become RB parallel to ZB. So only the ZB here is only beta RE, not using the emitter resistor because this is the bypass or short. So we got that ZI is 17.7 ohm. And then ZO is similar to RC is 2.2 kilo ohm. And then AV is minus RC per RE. So we got that minus 367.28. Yeah, please compare to this one. If we use the emitter resistor, we got that AV is minus 3.89, and here is minus 367.28. So see, this is the significant increase if we connect to emitter or bypass capacitor. So the bypass capacitor is very useful to increase the gain of the amplifier configurations. But the DC analysis is similar. And then why? Because the emitter resistor here is only useful only in DC analysis to prevent the instability of the beta. So if beta change, if we didn't connect to the emitter resistor, the collector current will change drastically. It's like I explained in the DC analysis or the BJT analysis, BJT DC analysis. But if we connect the emitter resistor here, if the beta change with the temperature, for example, so the collector current didn't change much. So we can prevent the invariability of the collector current because of the beta. But the emitter resistor is didn't useful in the AC analysis, because if we see from this calculation, the AV is very low. It's only minus 3.89. If we connect the bypass capacitor here, we can increase the AV by 100 times. So the bypass capacitor is very useful here. Okay, and then for Okay, and then for the last part of this week is the emitter follower configuration. Okay, in the emitter follower configuration, we connect the collector to the VCC directly without the collector resistor, and then the output is coming from the emitter here. This is the output, and then we connect to the emitter resistor. So this is also known as common collector configuration. So the another name of the emitter follower is common collector configuration. So the input is applied to the base, and then the output is taken from the emitter, and there is no phase shift between the input and the output. Emitter follower is also very useful as a buffer because of the AV is equal to 1. So the AV of the emitter follower is equal to 1. So the buffer is like we have the like this one. We have the amplifier, and then we will connect to the antenna here. Okay. So the buffer is prevent the signal coming to the system. So it's like the buffer. So it's like to prevent the signal coming from the antenna, like this one. And then another function of the buffer is to design the output impedance matching. So if we have the system here, this is another amplifier here, and another amplifier maybe has the high output impedance. So this amplifier has the output impedance is very high, and then we would like to match match with the antenna. Antenna typically has a 50 ohm or 75 ohm. So we have to match between the very high output impedance of the amplifier to very low input impedance of the antenna here. So we can use the emitter follower. So for emitter follower, the characteristic is emitter follower has the high input impedance here in Z1 here is high, but low output impedance. So we can make the matching condition between this amplifier before the emitter follower to the antenna. Okay, so this is another function. So if we draw the RE model of the emitter followers, become this one. So we have the RB here, and then beta RE, and then emitter resistor here, and then we didn't have the collector resistor between the collector to the VCC. So we connect the collector to the ground. Okay, and then the VO we measure the VO is between the emitter to the ground. Okay, so the input impedance here is I is RB parallel to ZB, and ZB is similar to emitter resistor. So ZB is beta RE plus beta plus 1 RE. So we got that ZB is beta dot RE. And then for the output impedance, ZO is RE parallel to small RE. So we got that ZO is RE, small RE, if the RE, emitter resistor, is larger than RE. Okay. And then for the voltage gain, we have the AV is VO per VI, RE plus small RE. So we got that if the RE is larger than RE, so we can remove this one. So VO is become the 1. Okay, for the current gain, AI is beta RB plus minus RB plus ZB. And then current gain for voltage gain is AI is minus AV ZI per RE. Okay. So so for the emitter follower, determine the RE, ZI, ZO, and AV, and then the repeat part if the RO, output resistance, is 25 kilo ohm. The first one RE, so we have to using the DC analysis. IB is VCC minus VBE per RB plus beta plus 1 RE is like the emitter resistor. Okay, emitter resistor configuration. So we got that IB is 20.42 micro ohm. And then IE is beta plus 1 IB. So we got that IE is 2.062 milliampere. And then RE is 12.61 ohm. So from here we can see see the RE is very small, only 12.61 ohm. And then the number B is ZI. ZI, we have to calculate the ZB first. ZB is beta RE plus beta plus 1 RE. So we got that ZB, because the beta, we can simplify like this one. Because of beta plus 1 RE is larger than beta RE, so we can, using the ZB is equal to beta plus 1 RE. And then, so the ZB is equal to beta plus 1 RE. And then, because of the beta larger than 1, so the ZB is become beta RE here. So this become beta RE. So we got that ZB is 334.656 kilo ohm. And then ZI is RB parallel to ZB. So we got that ZI is 132.72 kilo ohm. And then ZO is equal to RE here. So we got that ZO is 12.56 ohm. And then here we can see that if we want to make a matching condition between this amplifier to the antenna like this one. So if the antenna is 50 ohm, input impedance of the antenna is 50 ohm. So we have to match between the 50 ohm to the output impedance. So here, if the ZO is 12.56, it means that this is not matched. So we have to design that the RE is similar to 50 ohm. How we can design the RE is 50 ohm? So we can control the emitter current here. So if we decrease emitter current here from 2 to 0.5 milliampere, yeah, approximate about 0.5 milliampere, we got that RE is equal to 50 ohm. Okay, so here we can control the output impedance by control the emitter current here. Okay, so this is how we can easily using the emitter follower as a buffer or as for the matching condition output impedance of the system. Okay, then the AV is V over VI is, we got that AV is equal to 1. And then repeat if the RO is larger than 25. So we check the condition. RO is 25 kilo ohm, and then RE is 3.3 kilo ohm. So we got this 33 kilo ohm is not satisfied. Then we have to use this equation. ZB is become this equation, beta RE plus beta plus 1 RE per 1 plus RE plus RO. So we got that ZB is this one, 295.7 kilo ohm, and then ZI is RB parallel to ZB. So we got that 126.15 kilo ohm compared to the if we didn't have the R, if the RO is unlimited. And then ZO is similar, 12.56 ohm, and then AV is 1. Okay. Even though the condition of RO larger than 10 RE is not satisfied here, the result for ZO and AV is similar. Okay, but with the Z1 is only slightly less. Okay. So so in this condition for the emitter follower, we can ignore the effect of the RO. Because of we include the RO, the result is not very big a difference between we calculate the RO. Okay, so I think this is the all of this presentation for this week. We have 3 configurations: a voltage divider, common emitter, and then emitter resistor configuration, and then emitter follower or common collector configuration. Thank you very much for your attention. Let's we discuss later in online class. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh.